Okay, we're going to take a look at applications of trig functions. Okay, the first one we're going to look at is page 345, number 10 in the textbook. So I'm just going to put the question here under the camera, and then I will zoom in on it so we can read through the question here. Okay, so the question is about a pendulum. Okay, so a pendulum swings back and forth 10 times in 8 seconds. Okay, so a pendulum is like a swing. So if you're out in a swing and you're just sitting on it, it's not moving anywhere, that's kind of like where the axis is. And if you start swinging back and forth, well, you're acting like a pendulum. Okay, so this pendulum swings back and forth 10 times in 8 seconds. It swings through a horizontal distance of 40 centimeters. So basically, if you're looking at your shadow of yourself on the ground, if the sun was directly above you, the shadow would span about 40 centimeters. So 20 centimeters to the back as you swing back and 20 centimeters to the front as you swing forward. Okay, so that's a picture of what we're looking at here. So what they want us to do is to graph 2 cycles of this motion. So with distance, with respect to time, beginning with the pendulum at the end of its swing. So which end? It didn't say, so we'll just choose the most convenient end. And then determine the transformations necessary to transform a sine function to this graph. Okay, and then write the equation of this graph. So presumably in terms of sine. All right, so let's take a look at this. We'll write down the information that we have, and we'll do this. So a pendulum. Okay, so let's get the camera back here and back in focus. Okay, so a pendulum. So say that's the pendulum hanging down. That's the swing rope, say. And then the pendulum goes through a motion like this, back and forth. Okay, and from one end to the other for the rope of the swing. Okay, now this distance, this horizontal distance, they say is 40 centimeters. Okay, and we have to choose a starting point at one of the ends. So let's just choose this end as the starting point. Okay, so it's going to swing forward 20, backwards 20 for a total of 40 centimeters. Now, the time it takes to do one full cycle. So if it does 10 cycles in 8 seconds, okay, so let's see the time it takes for one cycle. So we're going to call that the period. Okay, so go through one cycle in the graph. So the period is 8 seconds for 10 cycles. Okay, and 8 divided by 10 is 0.8, so that's going to be the period. Okay, the time for one cycle, 0.8 seconds for one cycle. All right, so we want to graph this. So let's take a look at the graph. Okay, and they want 2 cycles graphed, so make it nice and long here. Okay, and the vertical axis. Okay, so this is the distance axis because the distance back and forth, and this is the time axis. Okay, and it's going to start over here, so call that positive 20 centimeters. Okay, so we're going to go from 20, and then it's going to go through 0 and then back to negative 20 and then back. Okay, so here is the axis, the t-axis, and the axis of the function. Now, it's going to go through, so we want 2 full cycles. So let's graph in marks here for quarter cycle. So let's do a quarter is there, so approximately another quarter, and another quarter, and another quarter, and that makes 4 quarters, so that will give me 1 full cycle. Starts at the top here, starts at 20 centimeters away, then swings back down, so it comes closer to here, and then goes to the back, so it goes to negative 20, and then comes back to the middle again. Okay, so right there, and then goes back to the starting point, which was out here. Okay, so now we join this together. Create a nice sinusoidal graph. And there is one cycle. And that one cycle of the graph takes 0.8 seconds. Okay. Now they want us to do another one. So do another 4/4 of a cycle. Okay. So it's going to come down here, then to the bottom, then back here, and then back up to the top. Okay, and that would be the graph that they're looking for part A. Okay, or a sketch of it. Now we got to come up with the equation of this function. Okay, so well, they want it in terms of sine, so d of t is a function notation for this. A sine k t minus c plus d. Okay, so this is a transformation of the sine function. So what are the transformations? Well, it could be a negative sign that's pushed forward, because a negative sign would start by going from the middle and going down. Okay, or it could be a positive sign. So we go back here, back to, so if that's 0.8, this is 0.4, this is 0.2, so that would be negative 0.2, be a quarter of a period. That would be 0.6, and so on. That would be at 1.6, because it's double. So if I went back here, this would be a sine graph shifted backwards. Okay, so then that would be a plus 0.2 in there. Okay, D is where the axis is, and the axis is right at 0, so that's going to be 0. Okay, and A, if it's a sine graph that's been moved back, A is going to be positive. The amplitude is 20. So C is going to be plus 0.2. So let's figure out what K is, though. So if we look at K, well, over here, the period is 2 pi of a regular sine function. Okay, the horizontal stretch factor is 1 over K. Remember, it's 1 over this value here. Okay, so the new period is going to be 1 over K times 2 pi, because it's being horizontally stretched by 1 over K. And 1 over K times 2 pi is just 2 pi over K. So that's the formula relating the period and this K value. Okay, K also represents the number of cycles there are between 0 and 2 pi radians. Okay, now if I want to find K, well, bring the K up and the T down, equals 2 pi, K equals 2 pi over T. And we know what the period is. The period is 0.8. So K equals 2 pi over 0.8. Now we could just divide this out and leave it as decimals, or we can make it as a nice fraction, because 0.8 is a nice fraction. The fraction is 4/5. 2 pi over 4/5. And when we divide by fractions, we flip the bottom one and we multiply. Okay, so that equals 5 over 4 times 2 pi, and that reduces to 5 pi over 2, and that would be the K value. So now we have pretty much everything to sub in here. Okay, so we have A, which is 20. sine. K is 5 pi over 2. Okay. And then t. And because it's a sine graph that's been moved back 0.2, I put a plus 0.2 in here. And d is 0, so we leave it like that. All right, so we have the equation of the function in terms of sine. Could we do it in terms of cosine? Okay. In fact, it's probably easier to do in terms of cosine because it starts at a maximum, and cosine always starts at a maximum. So cosine wouldn't have a horizontal translation. Okay, so the cosine graph for this would actually be much nicer. Still an amplitude of 20. Cos, and the period stays the same because the two functions have the same period. Cos and sine have the same period. And t, and no horizontal translation. Okay, so either of these would be fine to describe this graph, but the question asks for the one in terms of sine. Okay, that's it for that one.